Hello YouTubers, as promised we're going to be doing some math today. Um, Given the feedback I've gotten so far, I suspect that at least a handful of you would like to see some of this. But I'm going to start pretty simple, and my plan is maybe if I do a couple more of these that I'll increase the difficulty level as I go. So I'm going to start with just the simplest proof I know, and this is under the topic of proof by contradiction. Okay, and the reason why I'm doing this is because a lot of YouTubers are saying, well, how can you prove a negative, or you can't prove a negative, and I sort of want to explain that at least in mathematics we prove negatives all the time. So anyway, so we're going to just go ahead and give an example here. So what we want to look at is our prime numbers. Okay, hopefully if you've had a little education, you remember the prime numbers are all the sort of even whole numbers, or the whole numbers which are divisible only by themselves and 1. So that's 2, 3, 5, 7, 13, and so on. Okay, so the idea is numbers like 4, 6, 8, and 9 are not prime numbers, obviously, because they, like 4 is equal to 2 times 2, 6 is equal to 2 times 3, 8 is equal to 2 times 2 times 2, and so on. Okay, in fact, the fundamental theorem of arithmetic that's sort of like writing, states that all numbers can break down into a factor of into factors of primes. So you know, I know 144, for example, is equal to 12 times 12 equals whatever. That's 16 times 9, I guess. Right, but anyways, the point is it breaks down into the prime numbers 2 and 3 raised to some power, so that's 2 times 2, and so on. So that's the fundamental theorem of arithmetic, is that all numbers have a factorization that brings it down to product of primes. All right, and primes themselves have, of course, only one factor, if you ignore the ones, the multiplication by ones. Okay, so the question we have is how many primes are there? And you know, it has been suggested that there are infinitely many primes. So a simple question we have is, how do we know that there are infinitely many primes? Do we have some special generator for them? Do we have some sequence of them that we know exists that goes on forever? Or, I mean, how do we possibly know this? And so the way we're going to do this is this is the statement we're going to prove right here, that there are infinitely many primes, or we're going to test that statement anyways, and it's going to come out to be a proof. So the way that proof by contradiction works is we try to take the opposite point of view from what we think the truth is, and then we try to apply logic to it to see if that's self-consistent. If we show a certain point of view is inherently inconsistent, then we know it's not true, and so that leaves the truth must exist in the complement of that statement. Okay, so important. Remember remember this fundamental theorem of arithmetic, this is going to be an important step. So that all the numbers always break down into little primes like that. That itself is a statement that needs proving, but I'm going to ignore that for now. Okay? We all remember we're talking about prime numbers here. Okay, so we're going to start with our bad assumption. And I'm just going to use the geeky symbol here in the interest of brevity. So this is math speak. It means there exists less than infinite primes. That is, there exists finitely many primes. Okay, and that's my cheesy math propeller head speak for saying that. Okay, so this is a bad statement, right? This is our bad assumption, that there exists only a finite number of primes. So if there are a finite number of primes, it means that we can list them one way or another. And so we're just going to identify them by the symbols P1, P2, P3, and Pn. And this is going to be the set of all the primes. Basically, these are variable stand-ins for the numbers, 2, 3, 5, so on. And then we don't know what the largest prime is, but if there's a finite number of primes and there's some largest prime and there's some finite number of them n that we don't know, let's make that P1 instead of P0. I feel like Graham Chapman all of a sudden. Anyway, so we have n many primes. We don't know how many there are, but if it's finite, there must be some n, and there must be some largest one Pn. Like so, I put them in order, right, in terms of size, and these are just variable names that are stand-ins for the values 2, 5, 2, 3, 5, and so on. So the values 1 through n don't have any correlation other than they index the assignments the assignment we just made. So this is an assumption. Everything I'm doing so far here is well formed. There's no controversy and everything's fine, but it relies on this assumption that there are finitely many primes. So we suspect that if what we're doing here is wrong, that actually everything here I'm saying is wrong and makes no sense. But we don't know that yet. What we're doing here is we're testing an assumption. Okay, so I want to form the following expression. Okay, in math speak, dot means multiplication. Okay, so I'm just assigning a new variable here, x. What I'm doing is I'm taking the product. This is P1 times P2 times P3 all the way up to Pn. And then I'm going to add 1 to the end of it. Now, we know the values of some of these P's are like 2, 3, 5, and so on. So a simple statement we can make looking at this is say, well, this is kind of this is a number that's bigger than, say, each one of the P's. So we, in fact, want to explicitly make that statement here. And again, I'm going to use some more math geek notation. Okay. This value here that we've calculated, which is the product of supposedly all the primes, and then added, if we add 1 to it, that's certainly going to be larger than any one given prime. So that's what Pi is. And then, sorry, got cut off here. I'm trying to put the symbol for all here. It's for all I. Okay, so again, that's just math symbol. This expression is larger than Pi for any I that we pick. Now remember, we put this in order, the values here. So in fact, we're going to and change that and say that it's greater than Pn. Pn is the largest prime. So hopefully that's obvious, right? Because, I mean, if you want, you can just put Pn over on this side, subtract 1, show that that's positive. Okay, whatever. So this thing is clearly larger than that over there. Okay, so a simple question we can ask is, well, if these are all the Pn's, all the primes, then, you know, x must have a factor. Remember, by the fundamental theorem of arithmetic, we're thinking, well, x must have some factorization into smaller primes. And in fact, these are all the primes, so it must have some factor, at least some factor of a prime somewhere. So what we want to do now is go ahead and calculate x divided by pi, right, where I is some arbitrary index that we chose. And we see that, well, pi is going to be it's going to be one of the terms in here. So we imagine, like, if it's in the middle, it's going to be pi minus 1 times then pi plus 1 to Pn. Okay, so there's a pi in here that got canceled out. But the 1 on the end doesn't cancel with anything, really. So what we have here is the product of all the primes minus the pi. And then on the end we have 1 over pi. So this expression here is a nice integer. This is not an integer at all. It's 1 divided by some prime number pi. You know, and pi is not 1, it's some number 2 or greater. So that's a fraction. So this expression is not a whole number at all. So that means here on the other side, x divided by pi, it can't be a whole number, right? No matter, and this is true no matter what pi I chose, right? Even if I chose the first or last one, that just means this, you know, it's lopped off the end rather than the middle, but it doesn't matter. You'll always have this integer thing here plus some fraction round off. So this is not an integer. Oops. It's not. Some more math symbols there. This is not an integer. Anyways, I think the point is made. Now, if x does not have any factor pi at all, there's no pi factor in it at all, then that means it, but the fundamental theorem of arithmetic says that you have to have prime factors. In fact, it has to be able to factorize all the way down into primes. But if none of these pi are factors, then we have to conclude then x itself must be a prime. Okay? Or in fact, it must be a prime that's not in this list. So there, you know, therefore, x is a prime. Because the fundamental theorem of arithmetic says that all composite numbers break down into smaller primes. And this division here shows that no, there's no prime that could divide into it, so it can't break down into a sequence of primes. Therefore, x is prime. However, coming back to this statement here, we see that x was larger than the largest prime. So that means x is a prime that's not in this list. It's in some larger number. So now we're in trouble because we started with this list here, which we said was the list of all the primes, including the largest one. And just starting with that assumption alone, we were able to build another prime number x, which was even larger. That is a self-inconsistent system. And so more math geek symbols. That means we have a contradiction here. It's we can't have a finite set of prime numbers, because if we did, we could build one that was large. I mean, the set of prime numbers itself can't be just finite. Otherwise, we could always build one that's larger than the largest entry in there. We could always add a new one to it for any finite number, and so that's obviously inconsistent, so it doesn't make any sense. And so this counts as a complete proof, basically, that the number of primes is infinite, right? Now, you have to understand the structure of what we just did here. We started with a bad assumption, and then we applied all sorts of pretty reasonable analytical steps to it. Each of the steps was fine. The only thing that was in question was the assumption. But because the assumption was bleeding all the way through this thing, it meant that actually everything we're stating here is in some sense nonsense. Right? This is the point of a proof by contradiction, is that it doesn't establish more and more true things. Instead, it just shows that one certain thing, an assumption, is just completely false, or is false, because it is self-contradictory. So this is proof by contradiction, or reductio ad absurdum, as it was originally called in Latin. So, now that you all have this very simple proof in your minds, I'm going to ask 2 questions. Okay, and if you want, you can hit pause on the video player and see, if you can answer the questions, because I'm just going to ask the question and answer them immediately. So the first question is, what we demonstrated here is that this kind of finite list of primes cannot really exist. And then we leapt to the idea that, in our conclusion, that means that any list of primes would have to be infinite. So we'd have to have a sort of unending list of primes. This, of course, ignored one other possibility. And the question I have for you is, what other possibility is that? So you can hit your pause now and think about it. Okay, I assume you've hit unpause now. The answer is the empty set. There's a possibility that there are no primes. If there are no primes, then I couldn't even start to make these steps, obviously, and so these wouldn't be well-formed steps, and this wouldn't be well-formed logic, and therefore this wouldn't be a correct. But of course, we know that numbers like 2, 3, and 5 are primes, so we know the list is not empty. Okay. The second question I have is a little bit more insidious, and I'm going to go ahead and erase a little bit up here. Just leave that up there if you want. The second question I have for you is to look at the following expression. If you bring out your calculators or whatever, you can see that 2 times 3 times 5 times 7 times 11 times 13 plus 1, you calculate all that out, it becomes 30,031. And that number itself actually has a factorization of 59 times 509. These 2 numbers here themselves are prime, by the way. So the question is, wait, when we did our proof here, what we had done is we had taken the product of all these primes, added 1, and we created another prime. That was during our proof step, as you recall, or during our proof. So when I go ahead and do this, take this list of primes here, 2, 3, 5, 7, 11, 13, multiply them together and add 1, I ended up here with a number that isn't prime. So the question I have for you is, wait a minute, how could this step make sense here in the proof, and yet it clearly makes no sense if you just find ourselves a simple counterexample right here. So this is question 2. You can hit pause now. Okay, I assume everybody's hit unpause by now. The answer is remember that the original proof relies on a certain bad assumption. Assumption that this list of primes was the set of primes. That's why, although the steps make sense, so long as they mix in the assumption, the actual thing that they're stating is actually incorrect, right? So, or is not established. So when I said this is the product of all primes, I mean this isn't just a product of some primes. It's a product of all primes, right? That's how we established that it was prime, right? So, in particular, notice that the number 59 and numbers 59 and 509 are in fact larger prime numbers than 13, say. So, if 13 were the largest prime, well, then in fact we'd be set, but it's not, and that's where we see that happening. Anyways, that brings us to the end of this proof. I'm of course looking very forward to any kind of feedback that anyone wants to put. I mean, is this level okay? Is it too easy, too hard? Has this video gone too long? My God, it has. In any event, and just any thoughts you might have, I'd be very happy to hear. I'd like to thank everybody for listening.